This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
When you look back at the history of technology, there is almost always this expectation of a slow, steady, predictable march forward.
Right, yeah, like it's all mapped out.
Exactly. Like building a suspension bridge.
Right.
You lay the foundation, you string the main cables, you hang the suspenders one by one.
Yeah.
And everyone generally agrees it is going to take a specific, calculated number of years to reach the other side. I mean, you have industry roadmaps.
Oh, absolutely. Like Moore's Law.
Right. You have things like Moore's Law for classical silicon chips, which essentially dictated a linear, reliable progression of engineering for decades. We just expect progress to be a staircase.
It's comfortable to think of it that way, you know? We really like predictability in engineering.
We do.
We like knowing that the next smartphone will be exactly 20% faster than the last one, and that building a revolutionary new supercomputer is really just a matter of scaling up the existing blueprint.
But then you step into the world of quantum mechanics and quantum computing, and that entire linear roadmap just gets thrown out the window.
Completely thrown out, yeah.
Suddenly you have a team of researchers who figure out how to just, leap across the river. We are looking at a stack of research today that genuinely feels like someone found a cheat code for the timeline of human progress.
It really is a paradigm shift, and I know that term gets thrown around a lot.
But way too much.
Way too much. But in this specific instance, it is really the only accurate description. We're looking at a fundamental rewiring of how a quantum computer operates, from the atoms all the way up to the algorithm.
So, welcome to the deep dive. Today we are taking you, the listener, on a journey through a fascinating collection of highly dense, cutting-edge papers that are basically rewriting the rules of what the scientific community thought was possible in our lifetimes.
Yeah, it's incredibly exciting stuff.
It really is. We have research spanning quantum computing, Los Alamos National Laboratory, Harvard, MIT, Phasecraft, and the University of Nottingham.
A huge collaborative effort.
Massive. But the absolute center of gravity here, the focal point of this entire stack, is a landmark June 2026 paper and its accompanying press release. And it details a breakthrough called the transversal star architecture.
Right. And to give you the proper context on why this specific architecture is so monumental, you really have to understand the rather pessimistic assumption the broader tech community has been operating under for the last few years.
The idea that this was all science fiction for the next half century, basically.
Exactly. The general consensus, even among leading physicists, was that truly useful, fault-tolerant quantum computers, the kind that can actually design novel drugs or invent new battery materials, were decades away.
Right, because quantum states are incredibly fragile. We were talking about trying to perfectly control individual atoms.
Which is not easy.
No. So the narrative was that to do anything useful without the system crashing, you would need millions of physical qubits. You would need these massive warehouse-sized cryogenic facilities.
Yeah, and you would need probably 20 to 30 years of grueling incremental engineering just to get the error rates low enough to run a decent program.
And that was a mathematically sound assumption, right?
Yeah.
Based on the hardware architectures we were relying on at the time.
It was. The math was solid. But this team of researchers, led by Sheng-Tao Wang, Andrew Sornberger, and others, they just published a blueprint that essentially hacks that timeline.
Which is wild.
It is wild. They found a way to cut the required resources for useful quantum simulation by orders of magnitude. We are talking about executing complex operations 250 times faster.
250 times.
Yeah, using a fraction of the physical hardware and pushing us right to the brink of a totally new era in computation.
So our mission today is to unpack this, to follow the intellectual journey of these researchers. Like, how did they battle the microscopic physics to keep atoms from literally disappearing?
A massive problem, yeah.
Right. What was the massive mathematical roadblock they hit with something called magic states? And how did they ultimately solve it by abandoning the idea of a rigid microchip and completely reimagining the physical architecture of the hardware itself.
Because it is fundamentally a story about breaking down the walls between highly specialized scientific disciplines.
It's a collaboration story.
Exactly. It's about theoretical mathematicians, laser physicists, and software algorithm designers realizing they could no longer work in silos. They had to co-design this system together to bring us into what they are officially calling the mega-quop era.
Okay, wait, before we dive into the physics of lasers and atoms, I really want to challenge that term, because this field is notorious for its buzzwords.
Oh, absolutely.
We hear quantum supremacy, we hear quantum advantage, utility scale, but this paper explicitly introduces this term, the mega-quop era. What exactly constitutes a mega-quop, and why is it this magical threshold we are all suddenly racing toward?
It is essential to define our terms here because the stakes really rely on it. A quop is simply shorthand for a quantum operation.
Okay, quop, quantum operation.
Right. So a mega-quop represents 1 million reliable logical quantum operations executed sequentially without a fatal error crashing the entire system.
1 million. Now, playing devil's advocate here for a second, 1 million operations sounds incredibly small.
To a classical computer scientist, yeah, it sounds like nothing.
Right. If I open up a basic spreadsheet on my laptop, the processor is executing billions of operations every single second. So why is 1 million operations such a massive deal in the quantum world?
Because the nature of the operation itself is fundamentally different. And this is where human intuition often fails us, just because we are so used to classical computers.
We're used to binary, right? Ones and zeros.
Exactly. In classical computing, an operation is almost trivially simple. It is a transistor opening or closing. It is flipping a bit from a 0 to a 1. That's it. It's a binary switch.
On or off?
On or off. But in quantum computing, a logical operation is a continuous multidimensional rotation in a vastly complex mathematical space, what physicists call a Hilbert space.
So it's not remotely an apples-to-apples comparison.
Not even close.
It's
a single logical quantum operation on a sufficiently large number of qubits represents an exponential amount of computational heavy lifting.
Because it's exploring all those possibilities at once.
Basically, yeah. It is manipulating a probability distribution of potentially billions of different states simultaneously.
Oh, wow. Okay, so if you string together 1 million of those massively complex rotations without the fragile system collapsing, what actually happens?
You cross a very specific mathematical horizon. The mega-quop is the exact threshold where quantum computers stop being theoretical science experiments.
They stop being lab toys.
Right. It's the point where they stop being incredibly expensive laboratory novelties and begin executing calculations that are genuinely mathematically impossible for even the largest classical supercomputers on Earth to simulate.
It is the absolute tipping point for utility.
Yes. It is where you can start accurately simulating non-equilibrium quantum dynamics. It's where you can model the exact electron-by-electron behavior of highly complex molecules.
Things a regular computer just can't do.
Things that would take a classical supercomputer longer than the current age of the universe to calculate. A mega-quop scale quantum machine could do them in hours.
All right, so the mega-quop is the holy grail. But to understand how this Quera and LayNL team actually built the bridge to get us there with the transversal star architecture, we first have to look at the foundation they built it on.
The physical hardware.
Right. We have to understand the grueling, microscopic battles they fought just to make a single qubit function reliably. Because, you can't run 1 million operations if your very first one falls apart.
Exactly. You cannot build a massive, complex skyscraper if the foundational bricks you are using spontaneously crumble into dust.
Which brings us to the villain of this story, the fundamental fragility of the universe at the quantum level. Specifically, I want to look at the paper titled Achieving Optimal Distance Atom Loss Correction via Pauli Envelope.
Oh, that's a fascinating one.
It really paints this chaotic, almost violent picture of what it is actually like to work with a neutral atom quantum computer.
Yeah, to fully appreciate this, you have to visualize the sheer physical reality of what a neutral atom quantum computer actually is.
Right, because it's not a chip, is it?
No, not at all. In a classical computer, or even in an older superconducting quantum computer, you are etching circuits into a solid piece of material like silicon or sapphire.
The bits are physically nailed down.
Exactly. The physical bits are anchored. They are wired down. But a neutral atom computer is entirely different. You are taking individual neutral atoms, in the case of Quera's hardware. They use rubidium-87 atoms, and you are placing them inside an ultra-high vacuum chamber.
And how do they stay in place? I mean, you can't exactly wire down a single atom.
No, you can't. So you have to trap them using light. You use highly focused laser beams that act as optical tweezers.
Wait, okay, I need you to explain the physics of that for a second. How does a beam of light physically hold a piece of matter in place? Light doesn't have mass. It seems like trying to catch a baseball with a flashlight.
That's a great way to put it. It's a brilliant piece of physics, really.
Yeah.
It relies on the electric field of the laser light interacting with the atom.
Okay.
Even though the atom is neutral overall, the intense oscillating electric field of the laser induces a tiny dipole moment in the atom.
So this shifts the charges around inside the atom.
Exactly. The electrons get pulled slightly to one side, the nucleus to the other. This induced dipole then interacts with the gradient of the laser's intensity.
Oh, I see.
In simple terms, the atom feels a physical force pulling it toward the brightest part of the laser beam.
Toward the center of the beam.
Right. So if you focus the laser to a microscopic point, the atom falls into that focal point like a marble falling into a bowl. It is literally trapped by the light itself.
That is just incredible. So you have this grid of individual rubidium atoms, essentially levitating in a vacuum, held in place purely by laser light.
Yes.
But that sounds incredibly precarious.
It is incredibly precarious. Because they are just floating there, held by a microscopic bowl of light, things constantly go wrong. The environment is incredibly hostile at the quantum level.
What kind of things go wrong?
Well, a stray photon could hit the atom. A microscopic fluctuation in the laser's intensity could lower the walls of the trap. Or worst of all, the vacuum chamber isn't actually a perfect vacuum.
There's no such thing as a perfect vacuum, right?
Exactly. There are always a few stray background gas molecules floating around. And if one of those background molecules collides with your trapped rubidium atom, the kinetic energy literally knocks the atom right out of the optical tweezer.
Just bumps it right out of the bowl.
Yep. The atom falls into the vacuum. It is gone.
I was trying to think of a way to visualize this problem for you, the listener.
Yeah.
It is like trying to perform an incredibly complex, delicate symphony with 100 master musicians.
Oh, I like this analogy.
Right. Timing has to be perfect. The notes have to be exact. But every few seconds, a musician just spontaneously vanishes from the stage.
Just disappears.
Poof. Gone. Their chair is empty. Their instrument drops to the floor. How do you keep the symphony playing when the violin section keeps randomly disappearing?
And it's a huge problem. In recent physical experiments, this specific phenomenon, atom loss, accounted for more than 40% of the total physical errors in these systems.
40%. That's massive.
It was a massive bottleneck for scalability, because if you lose an atom, you lose the quantum information it was holding.
Right.
And in standard quantum error correction, losing a piece of data entirely is often far more destructive than just having that data get slightly corrupted.
Because it just leaves a hole in the math. So how did the experimental physicists solve this? How do you keep the symphony playing when the chairs keep emptying?
Well, they developed a theoretical framework they call the Pauli envelope, and practically they implemented a technique called mid-swap syndrome extraction.
Okay, I have to stop you there. I am familiar with the basics of quantum mechanics, specifically the Schrodinger's cat thought experiment.
Sure, the classic example.
Right, the whole idea is that a quantum state exists in superposition until you measure it. If you look at it, the wave function collapses.
You destroy the delicate quantum information just by observing it.
Exactly. So if the system is constantly losing atoms, how on earth are the researchers checking to see if an atom is missing without looking at it and thereby ruining the entire calculation? It sounds like a complete paradox. You can't look at the cake while it's baking, or it falls.
That is the exact paradox that makes quantum error correction so phenomenally difficult.
It seems impossible.
You are absolutely right. You cannot directly measure the data qubit to see if it's there. So the researchers had to be extremely clever. They figured out a way to perform what are essentially state-selective readouts using intermediate steps.
How does a state-selective readout bypass the measurement problem?
Instead of shining a light that interacts with the quantum data, they use a very specific frequency of laser light that only scatters off the atom if it is in a particular non-computational state.
Okay, but how does that tell them it's missing?
Well, more importantly, they use helper atoms called ancilla qubits. They briefly entangle the data atom with the ancilla atom in a very specific limited way, and then they only measure the ancilla atom.
Oh, So they are interrogating the helper, not the main data.
Exactly. It's like feeling the heat radiating from the oven door to know the cake is still baking rather than opening the door and looking at it directly.
That is brilliant.
Right. By checking these ancilla atoms during the error correction cycles, they can deduce if a data atom has gone missing without disturbing the quantum information held by the neighboring atoms.
So when they detect an empty chair in your symphony, they don't stop the music. They instantly flag it in the software. They know exactly when and where the loss occurs.
Yes.
Okay, but knowing an atom is gone doesn't bring it back. How does flagging it save the calculation?
This is where the mathematical framework of the Pauli envelope comes in. In quantum error correction, knowing that an error occurred and exactly where it occurred is more than half the battle.
Really? Just knowing where it is?
Oh, yeah. They proved mathematically that atom loss, which they term an erasure error, can be treated entirely differently than a standard computational error where the atom is still there but holding the wrong data.
Because it's easier to fix a known empty chair than to figure out if a musician is secretly playing the wrong note and ruining the harmony.
Precisely. If you know exactly where the error is, the threshold for correcting it is much, much higher. Once the system detects the loss, it doesn't panic. It relies on a reservoir zone of extra atoms like understudies waiting in the wings of the stage.
Oh, I see. They have backups ready to go.
Exactly. The system physically routes a fresh, newly initialized atom from the reservoir, moves it into the empty optical trap, and reintegrates it into the error-correcting code, all while the broader calculation continues seamlessly.
That is wild. They're swapping out parts of the engine while the car is driving down the highway.
They really are. And by doing this, they proved mathematically and physically that atom loss will not be the fundamental bottleneck that prevents neutral atoms from scaling up to the mega-quop era. They completely neutralized the biggest threat to the hardware.
Okay, so they stop the musicians from ruining the concert when they vanish. But what about when the musicians are actually playing?
Right, the actual operations.
Exactly, because keeping an atom in a trap is one thing, but forcing two atoms to interact and share quantum information is an entirely different beast. Let's look at the joint Harvard, MIT, and Quera paper on high-fidelity entangling gates.
This is where we see the heroic brute force effort of experimental physics. To perform a universal quantum calculation, you need to entangle two atoms. You need them to talk to each other.
And they don't naturally want to do that, right?
No. In a neutral atom system, because the atoms are neutral, they don't naturally interact very strongly when they are just sitting in their traps.
So how do you force it?
To make them interact, you have to hit them with a very specific, incredibly intense laser pulse to excite their outer electron into what is called a Rydberg state.
I was reading the breakdown of this in the sources, and the physical mechanics of a Rydberg state blew my mind. When the rubidium-87 atom gets hit by this specific laser and gets excited into this state, specifically what they call the N53 state, the atom's outer electron is pushed so far away from the nucleus that the atom physically swells up.
Yes, it balloons in size. The principal quantum number, n, determines the orbital radius of the electron.
Right.
When you pump that number up to 53, the radius of the atom scales by the square of n.
Meaning it gets massive.
Huge. The atom becomes thousands of times larger than its normal ground state. It becomes this massive, bloated, highly polarizable object on an atomic scale.
Yeah, why do you need them to be so huge?
Because when two adjacent atoms in the grid swell up like that simultaneously, their electron clouds essentially overlap. They exert massive dipole forces on each other.
They start pushing on each other.
Exactly. And because they are interacting so strongly, a fascinating quantum phenomenon occurs. One atom being in the Rydberg state physically blocks the neighboring atom from also entering the Rydberg state.
Wait, really? It just stops it.
Yeah, it's called the Rydberg blockade.
So they are so big, they literally crowd each other out.
Exactly. And that physical blockade mechanism is what the researchers use to create a controlled Z gate, or a CZ gate.
A logic gate.
Right, it's a conditional logic gate. The state of one atom conditionally controls what happens to the other atom. It is the fundamental operation that creates entanglement between the qubits.
So let me get this straight. You're inflating these atoms like massive balloons, using highly calibrated lasers, forcing them to touch and share information, and then deflating them back down to their ground state.
Yeah.
That sounds incredibly delicate.
It is arguably one of the most delicate operations in modern physics, because while the atom is inflated in that Rydberg state, it is incredibly vulnerable.
It can pop, essentially.
Well, it has a finite lifetime. It can spontaneously decay back to its ground state too early, ruining the gate. Or the laser light itself, which is intensely bombarding the atom, can cause unwanted scattering off of intermediate energy levels.
So you have to be fast.
Very fast. Every single microsecond the atom spends inflated is a chance for the delicate quantum information to leak out into the environment.
Speed is absolutely everything then. You have to get in, inflate them, entangle them, and get out before the universe notices.
Speed and extreme precision. To achieve this, the researchers utilized smooth amplitude laser pulses based on optimal control theory.
What does it mean, smooth amplitude?
Instead of just turning a laser on and off like a harsh square wave, they perfectly tailored the shape and intensity of the pulse. By doing this, they pushed the Rabi frequency, the speed at which they drive the atomic transition, up to an astonishing 17 megahertz.
So they are driving the atoms at a blistering pace.
Yes, incredibly fast. They used a complex two-photon excitation scheme. They hit the atom simultaneously with a 420-nanometer blue laser and a 1,015-nanometer infrared laser.
Two lasers at once.
Yeah, carefully balancing the frequencies to suppress any scattering from the intermediate states. It is a masterpiece of optical engineering.
And what were the actual physical results of all this laser gymnastics? Did it work?
The results were a world record for neutral atoms. They achieved a raw fidelity of 99.854% for these 2-qubit CZ gates.
Wow. Meaning that 99.854% of the time, the quantum gate executed exactly what it was supposed to do without introducing a fatal error.
Exactly. And it gets even better.
How so?
Remember the atom loss detection we just talked about? The Pauli envelope?
Yeah, checking for the empty chairs.
Right. When they applied that specific loss detection technique to select out the rare instances where an atom just happened to vanish during the gate, the fidelity of the remaining operations jumped to 99.941%.
That is staggering. We're talking about physical error rates of roughly 6 in 10,000 operations.
And here's the detail that truly proves we are ready for the mega-quop era. They managed to keep this highly calibrated, incredibly complex laser system stable, performing at that 99.8% fidelity for over 10 solid hours without needing any manual recalibration or alignment.
10 hours. Wait, why is that so significant? I mean, my laptop stays on for weeks.
Because in quantum time, where operations happen in nanoseconds and the environmental noise that the universe is constantly trying to destroy your system, 10 hours is practically a geologic epoch.
Oh, I see.
Yeah, in older systems, experimentalists would spend hours tuning the lasers only to have the system fall out of alignment in 20 minutes. 10 hours of stability proves that this isn't just a fleeting laboratory trick that requires a dozen postdocs hovering over the machine.
That's real hardware.
It is a robust, stable, industrial foundation for an actual functional computer.
Okay, I want to take a breath and consolidate this for a moment. We have established a foundation. The researchers have definitively proved they can build a reliable physical engine. The atoms stay in their traps, and when they interact, they do so with 99.9% perfection. But an engine, no matter how perfectly engineered, is totally useless if the car it's put into is simply too heavy to move.
That is exactly the realization the field came to.
Building a high-fidelity physical gate is a monumental achievement, but it is only step one. The real problem, the impossibly heavy car, is the software, the mathematics, and the architecture required for fault-tolerant error correction.
Right, the system overhead.
And this brings us to the massive math problem that stood squarely in the way of the mega-quop era, no matter how good the lasers got. We need to talk about the magic state bottleneck.
Ah, yes, the bottleneck.
I want to dig deeply into the mechanics of this because it's the core of why quantum computing has been delayed for so long.
To understand this bottleneck, you have to understand the fundamental rules of quantum error correction. As we've discussed, qubits are fragile. So we use codes, the most famous being the surface code, to protect logical information. We do this by spreading a single piece of logical data out across many, many physical qubits, creating a topological safety net.
So if one physical atom glitches, the collective group still holds the memory of what the data is supposed to be.
Precisely. But the strict mathematical rules of these error-correcting codes place a massive limitation on what kind of operations you can actually perform on that protected data.
The sources refer constantly to Clifford gates. What makes a Clifford gate so special?
Clifford gates are the standard, foundational operations that play nicely with quantum error correction. They belong to a specific mathematical group. The reason they are so important is that they are transversal.
Meaning what exactly?
This means you can apply a Clifford gate to a logical qubit by simply applying it to all the underlying physical qubits independently and in parallel.
Oh, I see.
The operation doesn't spread errors uncontrollably across the system. If one physical qubit has an error, applying a Clifford gate won't suddenly infect all the other qubits in the block. Clifford gates are safe. They are easy to protect.
Okay, so if they're safe and easy to protect, what is the problem? Just build a computer that uses only Clifford gates.
Well, here is the massive fundamental catch. Clifford gates are computationally weak.
Weak in what way? Like they can't do complex math?
There is a fundamental theorem in quantum information science called the Gotsman-Nil theorem. I'll explain it conceptually.
Please do.
Imagine a multidimensional sphere representing all possible quantum states. Clifford gates only allow you to rotate your state by 90-degree increments.
It's just up, down, left, right.
Exactly. You can only point to the poles or the equator. You can only point to very specific discrete coordinates on that sphere. Because you are only moving in rigid 90-degree chunks, the total number of paths you can take is highly restricted.
So it's not a continuous spectrum at all.
Exactly. And because it's so restricted, the Gotsman-Nil theorem mathematically proves that a purely Clifford-based quantum circuit can be perfectly, flawlessly, and efficiently simulated on a standard classical computer, no matter how many qubits you add.
Wait, hold on. Let me make sure I'm hearing this correctly.
Okay.
If you spend billions of dollars to build a hyper-advanced, cryogenically cooled, ultra-high vacuum laser machine, and you only run Clifford gates on it to keep it safe, it will do the exact same math at the exact same speed as my standard MacBook.
That is exactly what the math dictates.
That's insane.
A purely Clifford quantum computer provides zero quantum advantage. None. To get the actual quantum magic, to do universal quantum computation that can explore the infinite continuous space between those 90-degree points, you have to inject non-Clifford operations into the system.
And how do you do that?
The most common way to do this in a fault-tolerant architecture is by consuming a very specific, highly fragile quantum resource called a magic state. Usually, this takes the form of a T-gate, which allows you to rotate by 45 degrees, breaking the classical simulation barrier.
I was trying to come up with a good analogy for this restriction. Think about Clifford gates as the bread and butter of a sandwich.
Okay, I'm with you.
They provide the structure, they're cheap and easy to make, they fill you up, and they are reliable. But they are incredibly boring. You aren't winning any culinary awards with just plain bread and butter.
Very true.
The magic states, the non-Clifford gates, are like extremely rare, expensive white truffles. You only need a little bit of them, but they are what actually gives the sandwich its complex flavor. They are the ingredient that transforms it from a boring snack into a Michelin star meal that you couldn't get anywhere else.
I really like that analogy. It highlights the resource disparity perfectly. But here's the massive engineering problem. How do you get those pure, pristine white truffles? Because magic states, by their very mathematical nature, are not naturally fault-tolerant. When you try to create a magic state in the raw hardware, it is noisy, it is flawed, it has errors in it.
So if you inject a dirty truffle into your perfect sandwich, you ruin the whole meal. You corrupt the calculation.
Exactly. So you have to refine them, you have to clean them up. And you do this through a process called magic state distillation.
Distillation. Like refining oil.
Yeah, and this process is the bottleneck that was keeping us decades away from the mega-quop era. Distillation is a brute force, incredibly inefficient mathematical method. You take a huge number of noisy, low-quality magic states, and you basically sacrifice them.
You just throw them away.
You crunch them together through a complex quantum circuit to distill out one single, high-quality, pure magic state that is safe to use in your calculation.
It's like taking 1,000 cloudy, dirty drives of water, putting them through a massive filtration plant, just to get one crystal-clear drop out the other end.
That is precisely what it is. And the overhead, the cost in physical hardware and time is astronomical. In standard fault-tolerant architectures based on superconducting chips, the factories dedicated solely to distilling these magic states take up the vast majority of the physical space on the quantum processor.
So most of the computers just building these truffles.
Right. You might need tens of thousands of physical qubits just to run one distillation factory, and it takes an enormous amount of time to produce a single clean magic state.
And as I was reading the sources, it gets exponentially worse when you want to do quantum chemistry simulation.
Right.
Because you don't just need standard T-gate magic states, you need something called small angle rotations.
This is a crucial specific point for the applications we actually care about. If you were trying to simulate how a molecule evolves over time, say, to understand how a drug binds to a protein, the natural mathematics of that evolution requires turning the quantum state by tiny, continuous, arbitrary angles.
Like really tiny.
Like 0.001 degrees.
But you just said that standard fault-tolerant gates only allow you to turn the state in discrete chunks. The Clifford gates are 90 degrees, the T gates are 45 degrees. How do you rotate by 0.001 degrees?
Well, it's like trying to draw a perfectly smooth circle using only a very rigid etch-a-sketch. You can only go straight up, down, left, or right.
So you have to make thousands of tiny, jagged stair steps to the smooth curve.
Exactly. In quantum algorithms, this is called trauterization or gate synthesis. You have to synthesize that tiny, arbitrary angle by mathematically combining dozens or hundreds of standard distilled magic states.
Oh, man.
So now the overhead isn't just high, it's practically insurmountable for near-term hardware. You are taking the astronomical cost of distilling one magic state and you are multiplying it by 100 just to execute a single small rotation in your simulation.
Which means?
The math suggested you would need millions of physical qubits just to simulate a moderately complex molecule.
It's a complete traffic jam. So enter Chantal Wang, Andrew Sornborger, and their theoretical team. They look at this massive bottleneck, these warehouse-sized distillation factories, and they said there has to be a better way to do this.
Right.
And they proposed the original STAR architecture. STAR stands for Space-Time Efficient Analog Rotation. What was the core underlying idea of their initial proposal?
Their brilliant insight was to attack the fundamental inefficiency of synthesis. They said, let's stop trying to draw the circle with the etch-a-sketch.
To skip the stairs.
Let's stop relying entirely on discrete T-gates.
Yeah.
Let's find a way to inject the arbitrary small angle directly into the fault-tolerant circuit. They proposed a theoretical method that completely bypasses the massive, costly distillation factories.
How do you bypass distillation without introducing noise into the system? I thought raw magic states were dirty.
They are, but they bypassed it by using a probabilistic technique involving post-selection.
Post-selection.
Yeah, instead of building a massive factory to distill a perfect state, they would attempt to prepare the exact arbitrary small-angle magic state directly on a small, unprotected patch of physical qubits.
But that would be full of errors.
Right. Because it is not fully protected by the error-correcting code, this direct preparation is noisy and it often fails. But they designed a highly clever protocol where they can measure specific helper qubits and siliqubits again to definitively check if the preparation was successful or if an error occurred.
So they don't fix the errors, they just check for them.
Right. If the measurement yields the wrong result, indicating an error happened during preparation, they don't try to correct it. They just throw that state in the trash and try again.
They just start over.
They only proceed when the measurement confirms the state is clean.
They post-select the successes. It's like flipping a coin, trying to get heads. Instead of building a complex machine to guarantee the coin lands on heads every time, you just flip it normally, ignore all the tails, and only keep the heads.
Exactly. And because they are creating the small angle directly, they completely eliminate the need to synthesize it from hundreds of discrete T-gates. This original STAR proposal represented a massive theoretical savings in both time and space. The math was beautiful.
But there was a wall. The original STAR architecture hit a massive roadblock when they tried to map it onto actual hardware.
It did. And the wall was built entirely out of the assumptions they made about the physical hardware itself. The original STAR proposal was designed with fixed connectivity architectures in mind.
Like what?
Specifically, superconducting chips, which are the architectures championed by companies like Google and IBM.
Okay, I want to unpack the physics of fixed connectivity because it is crucial to understanding the final breakthrough. What does fixed connectivity actually mean when you were looking at a quantum processor?
Think of a superconducting quantum chip, like a traditional silicon-printed circuit board. The qubits are physical macroscopic objects, superconducting loops of metal etched permanently onto a sapphire substrate.
So they are nailed down.
They are physically wired down. Qubit is permanently etched next to qubit B. Therefore, qubit A can only ever directly interact with qubit B, C, D, and E, its immediate neighbors.
It can't talk to the other side of the board.
Right. It can never directly interact with qubit Z, which is etched on the opposite side of the chip.
Okay, so if I am running an algorithm and the math requires qubit A to share information with qubit Z to complete a calculation,
Sure.
How do you move the data?
You have to use a process called lattice surgery.
Lattice surgery.
Because the qubits can't move, you have to move the information through the qubits. It is essentially a microscopic bucket brigade.
Like passing buckets of water down a line of people.
Exactly. You have to pass the quantum state from A to B, then from B to C, then from C to D, all the way down the line across the entire chip until it reaches Z.
That sounds incredibly inefficient.
It is. It requires a massive grid of routing qubits whose sole purpose in life is to act as the buckets in the brigade, just holding space open so information can slowly propagate across the chip.
Just taking up space. And I imagine that bucket brigade takes a significant amount of time.
It takes a lot of time. And remember, the core mechanic of the star architecture, it relies on frequently mixing these post-selected analog magic state injections with standard fault-tolerant Clifford gates.
Right.
When the researchers modeled this on a fixed connectivity chip, they found that the time it took to route the information across the chip using lattice surgery was so devastatingly slow that it bottlenecked the entire process.
So the fast math didn't matter.
The speed of injecting the analog rotations was amazing, but the system constantly had to sit around, idling, waiting for the slow Clifford gates and the lattice surgery bucket brigade to catch up.
The engine was revving at 10,000 RPM, but they were stuck in bumper-to-bumper traffic.
Precisely. The rigid, physical, fixed connectivity of the hardware completely negated the theoretical mathematical advantages of the star protocol.
It seemed like a brilliant idea that was just doomed by the reality of solid-state physics. It was a dead end.
But here's where the story shifts.
Because the team at Quera and LANL looked at this traffic jam, and they realized something profound. They realized they didn't need to write a better routing algorithm. They didn't need to optimize the bucket brigade.
They needed to stop thinking about quantum hardware as a rigid, static microchip. They needed a physical architecture that inherently matched the fluidity of the math.
And this brings us to the absolute core breakthrough of the June 2026 PRX quantum paper. This is where the neutral atom platform we discussed earlier changes the entire paradigm of computing.
Completely changes it.
Let's talk about the concept of flying atoms, because when I read that in the paper, it sounded like straight-up science fiction.
It is the aha moment of the decade. Remember that in a neutral atom processor, the qubits are not etched into metal.
Right, they are floating.
They are not wired down to a circuit board. They are individual atoms held in a vacuum by optical tweezers. Now, modern neutral atom arrays use two distinct sets of lasers to manage these tweezers.
Okay, two sets.
First, you have static traps, which are created by a spatial light modulator, or SLM. The SLM acts like a holographic projector, creating a fixed, stable grid of light traps. This holds the atoms in their stationary memory positions.
That makes sense.
But then you have a second set of lasers. These are moving traps generated by devices called acousto-optic deflectors, or AODs.
Okay, stop there. I need to know the physics of an AOD. How does a laser beam, which travels in a straight line, suddenly pick up an atom and move it around like a tractor beam?
It's a fascinating piece of technology. An AOD consists of a transparent crystal. You attach a piezoelectric transducer to the crystal.
Wait, a transducer, like a speaker?
Exactly like a speaker. And you drive it with a high-frequency radio wave, sound waves, essentially.
So you're playing sound into a crystal.
Right. These sound waves travel through the crystal, creating areas of compression and rarefaction. This acoustic wave acts as a diffraction grating for the laser light passing through the crystal.
Oh.
By slightly changing the frequency of the sound wave, you change the spacing of the grating, which physically changes the angle at which the laser beam exits the crystal.
So by playing a different note of sound into the crystal, you can steer the laser beam in real time.
Exactly. And you can steer it smoothly and incredibly fast. The AOD allows you to literally grab a subset of the data atoms from the static SLM grid, say, an entire column or a specific block of qubits, and physically fly them across the processor in a matter of microseconds.
While they are holding the quantum data?
Yes. You maintain their delicate quantum coherence the entire time, and you place them down right next to completely different atoms on the other side of the array.
Okay, this is wild. Think about the lattice surgery bucket brigade on the rigid superconducting chip. It is like a slow, whispered game of telephone down a very long line of people standing rigidly in a hallway. It takes forever for the message to propagate from the front to the back.
Yes.
What the AOD moving traps allow you to do is completely demolish the hallway and replace it with a giant dance floor.
I love this.
If the person at the front of the room needs to talk to the person at the back, They don't whisper it down the line. They just glide smoothly across the dance floor, swap partners, whisper the message directly into the recipient's ear, and glide back instantly.
That is a phenomenal physical analogy. You are replacing routing with physical transport. And the mathematical term for that dance floor maneuver is a transversal operation.
Transversal.
By physically moving the atoms, the researchers realized they could perform transversal Clifford operations on entirely different blocks of logical qubits.
Dig into the math of transversal for us. Why is that specific word so important here?
Transversal means you are performing operations in parallel, directly between the corresponding physical qubits of two different logical blocks. Because the atoms can literally fly to wherever they are needed, you completely bypass the bucket brigade.
So no more routing qubits.
You don't need a massive space-consuming grid of dedicated routing qubits just sitting there taking up space. You just pick up logical block A, fly it over to logical block Z, interact all their constituent atoms simultaneously in parallel, and then move block A back to its memory zone.
It completely eliminates the lattice surgery overhead.
Entirely. It erases the traffic jam. And that solves the fatal flaw of the original star proposal.
Because now it's fast enough.
Exactly. By using flying atoms, the speed of executing the fault-tolerant Clifford operations suddenly matches the incredible speed of the post-selected magic state injection. The hardware finally aligns with the math.
And they named this newly aligned, co-designed approach transversal star. So what does this actually mean for the performance of the machine? Let's get into the hard numbers, because the paper and the accompanying press release drop some figures that completely upend the industry roadmaps.
The numbers are exactly what put us on the threshold of the mega-quop era today, rather than in 2040. By co-designing the star algorithm directly with the flying atom hardware capabilities, they calculated that this approach delivers up to 250 times faster execution speeds compared to conventional, fixed connectivity, fault-tolerant architectures running standard lattice surgery.
250 times faster, so a molecular simulation that might have taken a month of continuous uptime now takes a few hours.
Exactly. But the speed is only half the victory. Because you no longer need the massive grid of routing qubits, and because you have completely eliminated the need for those warehouse-sized magic state distillation factories, it drastically cuts the physical hardware footprint required to run the machine.
How drastically? Like by half?
Let me give you the specific benchmark they use in the paper. In quantum computing, we calculate something called a simulation volume. This is a metric that combines the size of the quantum system you are simulating with the depth how long you can simulate it for without errors overwhelming the data.
Okay, size and length.
Right. A simulation volume of 600 is deep into the beyond classical mega-quop regime. To reach that volume using standard methods on a fixed connectivity chip, you would need to synthesize and execute over 1 million, perhaps 10 million, perfectly distilled T-gates.
Which would require an astronomical amount of physical hardware just to run the distillation factories. Millions of physical qubits.
Millions, exactly. But with the transversal star architecture, bypassing distillation and bypassing routing, they calculate that to reach that exact same simulation volume of 600, you only need about 10,000 physical qubits.
Wait, 10,000. That's it?
That's it. And crucially, you only need them operating at a completely reasonable physical error rate of 1 in 1,000.
10,000 physical qubits. That is not a decades away science fiction number. That is a number that leading hardware engineers are actively aiming for in their next few roadmap cycles.
It takes the distant horizon of useful, fault-tolerant quantum computing and brings it rushing toward us at breakneck speed.
But, and this is where the story gets truly crazy, they didn't stop there. A twofold space savings and a 250 times speed up is an absolute triumph. Most research teams would publish that, collect the rewards, and go home.
Right, they'd be done.
But these researchers asked a fundamental engineering question. If we have already solved the physical routing problem by making the atoms fly, how much further can we push the math?
Right, they solved the traffic jam on the highway. Now they wanted to upgrade the vehicles themselves, and that brings us to the integration of QLDPC codes, which are detailed in the contrast to it, towards ultra-high rate and magic tricycles papers included in our stack.
Okay, QLDPC, Quantum Low Density Parity Check Codes. I see this acronym constantly in the advanced literature. What exactly are these codes, and why are they considered the holy grail of quantum error correction?
Well, up until now in this conversation, we've implicitly been talking about the surface code. The surface code is the industry standard for a reason. It is geometrically simple. It only requires atoms to talk to their immediate nearest neighbors on a 2D grid. Because it's simple, it's easy to build, but it is horribly inefficient.
Why is it inefficient?
It has what we call a low rate. As you scale up the size of your logical qubit to make it more secure, the number of physical qubits required grows quadratically.
I picture it like trying to ship a fragile wine glass in the mail. The surface code is like wrapping that glass in 20 layers of standard bubble wrap. It is undeniably safe, but the bubble wrap is so bulky that it takes up an enormous amount of space in the shipping box.
Exactly. The overhead is massive. QLDPC codes are advanced mathematical codes that are fundamentally different. They belong to a class of high-rate codes. Through incredibly complex mathematical hypergraphs, they can pack vastly more logical qubits into a much smaller number of physical qubits while maintaining the exact same level of protection against errors.
So following the analogy, instead of 20 bulky layers of bubble wrap, QLDPC codes are like a hyper-advanced microscopic titanium scaffold that encases the glass. It provides perfect protection, but it uses a tiny fraction of the material in space.
That is a very apt visualization. But if QLDPC codes are so mathematically superior, why isn't every quantum computing company using them already?
That was exactly my question when reading the papers. If they are better, why aren't they the standard?
Because that titanium scaffold is dizzyingly complex to build in reality, the math of a QLDPC hypergraph requires long-range, crisscrossing connections between qubits that are very far apart from each other.
Of the fixed wiring problem again.
Right. If you try to map a QLDPC code onto a standard fixed connectivity superconducting chip, it is an absolute physical nightmare. The microwave routing wires would have to cross over each other thousands of times in 3 dimensions.
Which would just short out, basically.
The physical crosstalk, the interference, and the sheer engineering impossibility of wiring it all together make it practically useless for solid-state architectures.
But we aren't using solid-state architectures anymore. We don't have wires.
Exactly. We have flying atoms.
The acousto-optic deflectors. The dance floor.
This was the brilliant synthesis of the research. The team realized that the dynamic reconfigurability of the neutral atoms, the ability of those AOD lasers to pick up groups of atoms and perform complex X, Y, and Z cyclic shifts across the entire array, was the absolute perfect physical match for the complex routing requirements of QLDPC codes.
Because they can just move to where the math says they need to be.
Yes. The atoms can just fly to wherever the mathematical hypergraph dictates they need to be, interact, and fly back. The long-range connections are solved by physical movement.
So they extended the transversal star architecture. They swapped out the bulky surface code for these highly efficient QLDPC codes. What was the final result on the hardware requirements?
Remember how standard transversal star cut the physical qubit count down to an incredible 10,000? By integrating the high-rate QLDPC codes into the flying architecture, they reduced the physical qubit count by a further factor of 5.
Wait, so they divided the 10,000 by 5.
Yes.
So we are now talking about doing mega-quop scale, beyond classical fault-tolerant quantum simulations with only 1,500 to 3,000 physical qubits.
That is exactly what the research dictates, 1,500 to 3,000 physical qubits.
It's just, I really have to pause and emphasize the sheer elegance of this to you, the listener. It wasn't just a hardware fix like building a slightly more powerful laser. And it wasn't just a software fix like writing a slightly more efficient line of code.
Oh, it's much deeper.
It was the profound realization that the algorithm, the star architecture, the error-correcting math, the QLDPC codes, and the physical constraints of the hardware, the flying neutral atoms, all had to be co-designed together as one living, breathing, deeply integrated system.
It is the ultimate manifestation of hardware-software co-design. When you align the fundamental physics of the machine with the theoretical mathematics of the code, the resource requirements don't just decrease, they absolutely collapse.
Okay, so what does this all actually mean for the world? We have spent the last half hour talking about the esoteric physics of rubidium atoms, the abstract math of magic states, and the acoustic waves of laser tweezers.
Right.
But why should you, the listener, care about any of this? Why is the race to the mega-quop era so critical for the future of humanity? Abstract math and world records in physics journals are great, but curing the incurable is better. I want to pivot to the human element of this story and bring in the final paper in our stack, the Nottingham Phasecraft Quera, or NPQ framework paper.
This paper provides the critical why behind all of this intense engineering and mathematical optimization. The researchers at the University of Nottingham, working alongside algorithmic experts at Phasecraft, are targeting a very specific, devastating biological disease called myotonic dystrophy type 1, or DM1.
What exactly is DM1, physically and biologically?
DM1 is the most common adult form of muscular dystrophy. It is a severe genetic disorder. Biologically, it is caused by an abnormal expansion of a specific DNA sequence, which leads to toxic RNA that traps essential splicing proteins in the cells.
What does that do to the body?
The result is progressive, debilitating muscle wasting and weakness. It causes severe cataracts and fatal heart conduction defects. It is utterly devastating for the patients and their families. And the tragedy is that currently there are absolutely no disease-modifying treatments available. It is considered incurable.
Why is it incurable? I mean, we have massive pharmaceutical companies and supercomputers running AI drug discovery around the clock. What is the holdup in the drug discovery process for this specific disease?
The holdup is entirely computational. It is a physics problem masquerading as a biology problem. To create an effective drug for DM1, researchers are trying to design something called a covalent inhibitor. This is a specific type of drug molecule that binds to its biological target, the toxic RNA structure, by forming a covalent bond.
Explain the physics of a covalent bond. Why is that different from how normal drugs work?
Most drugs work through weaker non-covalent interactions. They fit into a pocket on a protein like a key in a lock, but they can fall back out. A covalent bond is fundamentally different. It means the drug molecule actually shares its electrons with the target molecule, creating a permanent, incredibly strong, irreversible molecular lock. It chemically welds the drug to the target.
Like superglue at a molecular level.
Exactly. But to rationally design that superglue, you have to precisely simulate how those electrons interact and form that bond. You are simulating fundamental quantum mechanics. And this is where classical computers hit a brick wall. Covalent bonds involve strong electron correlations. The electrons are highly entangled and their states depend entirely on each other.
And classical computers can't model entanglement.
Right. Classical supercomputers use approximations, usually something called density functional theory, or DFT. But for strong electron correlations in covalent bonds, classical DFT simply fails. The math is too complex, the approximation breaks down, and the simulation gives you the wrong answer. You end up synthesizing a drug in the lab based on a flawed computer model, and it fails in testing.
So to simulate a complex quantum biological process, you fundamentally need a quantum computer.
Yes. Richard Feynman famously predicted this exact scenario back in the 1980s. If you want to simulate nature, you need a machine that operates on the rules of nature. But the MPQ team isn't just sitting around waiting for a perfect millions of qubits machine to be built in 20 years. They have developed a highly pragmatic hybrid framework called Quantum Enhanced Density Functional Theory, or QEDFT.
How does a hybrid framework work? Are they somehow using the transversal star architecture to design this DM1 drug today?
Not today. They are preparing the software pipeline for it. Right now, they're cleverly splitting the computational workload. They use classical supercomputers to do the heavy lifting of modeling the large-scale, easy parts of the molecular structure, but they algorithmically carve out the specific, highly complex quantum interaction zone, the exact active site where the covalent bond forms between the drug and the RNA. They isolate that incredibly complex piece of math, and they target that specific chunk for quantum simulation.
But since they don't have a fault-tolerant mega-quop machine quite yet, how are they testing this hybrid pipeline? How do they know it works?
They procured an NVIDIA H200 server utilizing 8 state-of-the-art GPUs running in parallel, specifically to perfectly emulate a 36-qubit quantum computer.
Wait, I really want the listener to grasp the scale of that. It takes 8 state-of-the-art, incredibly expensive supercomputing GPUs running at maximum capacity just to fake the mathematical output of 36 atoms.
It really puts the immense exponential power of quantum mechanics into perspective, doesn't it? 36 atoms hold more complex state information than millions of classical transistors can easily process. They are using this 36-qubit emulation to run what's called a variational quantum eigensolver, or VQE algorithm. Through this, they're gathering massive amounts of highly accurate quantum data about how these specific covalent bonds form.
And what do they do with that emulated quantum data?
They feed it back into the classical system. They use it to train classical neural networks to correct the errors in the standard DFT models. They're essentially injecting quantum-level accuracy into classical drug discovery algorithms. The beauty of this MTQ framework is its plug-and-play practicality for the pharmaceutical industry.
Meaning what, exactly?
Meaning a computational chemist working in a pharmaceutical lab trying to cure DM1 doesn't need to go back to school to get a PhD in quantum physics or laser optics to use this. They can just run their standard, familiar drug design workflows on their computers, and behind the scenes, the QEDFT framework seamlessly provides them with quantum-enhanced accuracy for the hardest parts of the molecule. It completely bridges the gap between quantum physicists and biological chemists.
And this brings us full circle. To tie everything together, this drug discovery pipeline is the ultimate real-world payoff of the transversal star architecture. Right now, the Nottingham team is forced to emulate 36 qubits on an NVIDIA server because near-term quantum hardware is too noisy. But to actually design the final perfect covalent inhibitor for DM1, they need more qubits, and they absolutely need them to be fault-tolerant.
Exactly. The transversal star architecture and the incredible space and time savings it mathematically provides by flying atoms around is the physical blueprint that will allow hardware manufacturers like Quera to build systems like their upcoming Gemini-class processors that can actually run these molecular simulations natively at the mega-quop scale.
They will be able to run it on those 1,500 to 3,000 physical qubits we talked about earlier, rather than waiting for a million qubit machine.
Yes. Transversal star is the bridge. It gets us from emulating 36 qubits on classical servers today to running perfectly fault-tolerant, disease-curing simulations on actual quantum hardware tomorrow, effectively skipping decades of expected linear hardware engineering.
It takes the highly abstract math of magic states and the mind-bending physics of flying atoms in a vacuum chamber, and it translates them directly into finding cures for untreatable genetic diseases. Yeah. It is breathtaking when you look at the whole picture.
It really is.
So I want to take a moment to step back and summarize the intellectual journey we've taken today. We started at the absolute microscopic limit of the universe. We watched researchers battle the fundamental fragility of nature, figuring out how to use complex quantum error correction and state-selective readouts to keep the computational symphony playing, even when rubidium atoms literally vanish into the vacuum.
We saw the experimentalists achieve an unprecedented 99.9% control over the entanglement of these atoms, pumping them into massive Rydberg states using incredibly precise 17 megahertz optimal control laser pulses and keeping that delicate, hypersensitive system completely stable for 10 hours at a time.
We watched the theoretical computer scientists run headfirst into the magic state bottleneck, the crushing realization that doing complex, universal quantum math via magic state distillation was just too physically expensive and slow to ever work on traditional, rigid superconducting chips. And then we saw the ultimate breakthrough, the profound realization that if you abandon the concept of the rigid microchip altogether and use acoustic waves to let the atoms physically fly across a processor, you can perform transversal operations that instantly clear the mathematical traffic jam,
resulting in a system that speeds up operations 250 times, cuts the physical footprint in half, and then, by applying the hypergraph math of QLDPC codes, cuts the hardware requirement by a factor of 5 again. It brings the horizon of the mega-quop era down from millions of distant qubits to just a few thousand achievable physical atoms.
And they did all of this with the ultimate guiding goal of modeling the most complex molecular bonds in nature to rationally design covalent drugs to cure devastating genetic diseases like myotonic dystrophy.
If we pull back and connect all of this to the macro level, I want to leave the listener with a final thought to really mull over. For the last 50 years, the entire global tech industry has relied heavily on the concept of abstraction. A software engineer writing an iPhone application today doesn't need to know how the physical silicon transistors inside the processor actually work. The hardware and the software live in completely separate, walled-off worlds. The hardware is a black box.
Right. Abstraction has been the undisputed secret to scaling the digital age. You specialize, you abstract, you build on top of the black box.
But quantum computing is currently proving the exact opposite philosophy. The transversal star breakthrough, this massive leap across the timeline of human progress, only happened because the theoretical mathematicians, the laser physicists building the hardware in the lab, and the software algorithm designers actively broke down the walls between their disciplines. They couldn't rely on abstraction. They had to understand each other's worlds deeply, intimately, to co-design the system from the ground up. The algorithm had to understand the physics of the optical tweezers.
So in our hyper-specialized, highly abstracted modern world, it raises a really important, provocative question.
Exactly. How many other massive timeline hacking breakthroughs in science, in medicine, and clean energy are just sitting there waiting for us to stop treating hardware and software, theory, and physical practice as totally separate, abstracted worlds? What else can we achieve when we start co-designing our solutions holistically, from the underlying physics of the atoms all the way up to the mathematics of the algorithms?
It makes you wonder what other seemingly impossible bridges we could just leap right over if we stop building them one standard brick at a time. Thank you for joining us on this deep dive. Keep exploring the research, keep questioning the accepted roadmaps, and keep an eye on those invisible forces and those flying atoms that are actively shaping our future. Until next time. Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.